Dear students, I am Dr. Abhishek Sharma and this is the part 3 video for PCM. In this video we will discuss encoder and its working, transmission path and PCM receiver. Now start discussion. Encoder, this is the purpose of the encoder is to make transmitted bits more robust to noise, interference and other channel losses. Encoder is usually convert the input quantized value into its equivalent binary bits. For example, consider this figure. This is an analog low pass message which is transmitted through a sampler, and after sampling, this is the ideal sampled signal. The sampled voltage will be 1.2. This is a case which is discussed in this scenario. This is not a final case. There are several other cases that depends upon the output depends upon the quantization process. Suppose this voltage is 1.2 and this is 2.73, this is 2.6 and this is 1.35, and the ideal sample signal is then passes through a quantizer. It will give the this is an assumption, and assumption is based on that quantizer is converting the input sampled values to its nearest decimal values. I have considered this, that my quantizer is converting and is taking greatest integer function. That means not greatest integer, least integer function. 1.2 is converted to 2.0, 2.73 is converted to 3 and so on. Now after converting this sampled signal and to a quantized value, 2 is passed, the sample voltage is passed through encoder, and encoder converts this 2 is in its equivalent binary bits. For example, if the encoder is of 3 bits, then the equivalent output will be 0, 1, 0, that's it. And then after 2 the voltage 3 is transmitted, then the equivalent value will be 0, 1, 1, 0, 1, 1 and 0, 1, 0 and so on. This is the transmitted data after the encoder. Now the total number of levels that can handle by this 3-bit encoder is 0 to 7 volt. Okay, for example, this is 0, 1, 2, 3, 4, 5, 6, 7 and this is your binary equivalent for 3 bits, as I've already discussed here. Now there is a problem. You can say that there is a problem because of the band limited nature of the channel. What happens is these bits, due to the noise and band limited channel response, the pulse get distorted, and because of the band limited nature of the channel, the pulse becomes interleaved to each other. This is called ISI. It happens in time domain. I will discuss it further, but right now, to avoid distortions, for example time distortion, we will introduce 2 guard times. One is word guard time and second is bit guard time. Bit guard time is introduced between 2 bits. For example, 0, 1, 0 is transmitted and 0, 1, 1 is transmitted afterward. This is a single word. This word is equivalent to a sample value that was 2 volt and 3 volt. Now what happened, to separate these words in channel, we will allow some word guard time in between them. Similarly, to distinguish 2 bits 0 and 1 or 1 or 0 and so on, we will also introduce a bit guard time. So there is 2 guard time in this case. First is bit guard time and word guard time. To distinguish 2 words, we will use word guard time, and to distinguish 2 bits in a single word, we will use bit guard time. Okay, then this is again a PCM transmitter block diagram. Here we use anti-aliasing, sampler, and quantization. Sometimes the quantizer and encoder is same block is in the process of quantization and encoding is in the same block. So don't worry about it. You can also write that the output of the PCM will be in form of bits in this case, or you can also use another block diagram after quantizer, and that block diagram is encoder. In several books, several literature, you will find that quantizer and encoder belongs to same block. This is simple A to D conversion. This is the PCM output. Okay, then now transmission path. Transmission path is a path which connects your transmitter with your receiver. Generally, pulse code modulated data is transmitted through wires because there is no involvement of carrier. I have already said earlier that PCM is a baseband digital transmission. We do not use any carrier to shift the spectrum from origin to FC. So in general, the PCM is transmitted via wires. Most of the computer connection, one computer to another, is performed in terms of PCM. So transmission path also play a dominant role. In transmission path, regenerative repeaters are used to improve the PCM signal while transmission. The block diagram of transmission path is also shown in figure. So let us suppose due to the noise of the channel, our pulse get distorted and it look like this. Then regenerative repeaters does it can again re-smooth the pulse and store in the same which was transmitted earlier. For example, this is 1, and the conversion technique also actually the regenerative repeater uses some sort of comparators in the circuit, and what comparator does is compare incoming voltage. It compares the incoming voltage with the threshold voltage, for example this pulse, and if this pulse is greater than, this is suppose your MT, if your MT is greater than VTH, then your output will be positive VCC or V, and this is your VCC, and this is your minus VEE. You know that if your MT is greater than VTH, the output is VCC. That is happening here. If the pulse is greater than threshold levels, then the output will be 1. If the input is 0 less than threshold level, the output is 0. And again the pulse is again greater than threshold level, the output is restored to 1, and so on. So what repeater is doing? Repeater again actually it cures the input distorted data. Okay, there are several stages of regenerative repeaters that depends upon the incoming data. Okay, then the most important feature of PCM is to control the effect of noise and distortion produces in transmission path. There are basically 3 steps performed by the repeaters. One is equalization. Its function is to shape the received pulse, which I have already discussed earlier. This is pulse shaping. The regenerative repeater is just restore the pulse shape and equalized. Okay, receive pulse so as to compensate the effect of amplitude and phase distortion. Noise generally affect the amplitude and phase. Phase is related to shifting of the pulse in time domain. Now there is another important part, which is timing circuitry. Timing circuitry provides a periodic pulse train derived from the receipt pulses. We can also consider timing circuitry, because please try to understand this in the way that try to understand. For example, how can a receiver know that one is started from, suppose, T1 and end it at T2? How can a receiver know? So receiver, there is a very important information which is called timing information of the signal. Timing information gives the timing information of the signal, gives the knowledge of to a receiver that what is the bit duration of a single bit, where it starts and where it ends. If receiver and transmitter is not synced, then receiver cannot recover the exact data. Okay, then decision making. For this decision making at particular instant of time, the circuitry determine on whether or not the amplitude of the quantized pulse noise exceeds a predetermined voltage called threshold voltage. This is your threshold voltage. In this figure I have already told you, this is the threshold level. If the pulse is greater than threshold voltage, the regenerative repeater represented by 1, and if it is less than 0, threshold value is greater than the incoming pulse, then it restored to 0, and so on. Okay, then PCM receiver. PCM receiver is the most important section, because if you want to reconstruct your input which is transmitted by the transmitter, so you have to use PCM receiver. PCM receiver is shown in the figure. It have a regenerative circuit, a decoder, and a reconstruction filter. Generally, reconstruction filter is not special, it is a simple LPF, low pass filter. Final operation of the receiver is to recover the message. Pulse are passed through a decoder which converts it into equivalent decimal value. Output of the decoder is passed through a reconstruction low pass filter having cutoff equal to message bandwidth. Now we have already know the regenerative circuit. The decoder is already studied in digital electronics, then how encoder and decoder works. Reconstruction filter is an LPF filter which reconstructs the sampled the decoded value, which is the, for example, 0 1 1 is going inside the decoder. The decoder gives you output 3.3.0 and so on. Decoder converts these bits into again quantized values. So after applying this value to reconstruction filter, it gives the output, which is equivalent to your message empty. Actually there is a little bit difference, and you can say because of the quantization noise, empty is not exactly recovered. It is recovered as like this m cap t, which is either you can say nearest recovered signal by this PCM to the empty. In general, for a single tone, you can easily recover this with the help of reconstruction filter. Okay, then what is ISI? As I have already told you that our channel is a band limited channel. Band limited means band pass. This is a channel response. This is, suppose this is F1, this is F2, this is F, this is H of F, magnitude response for a, what happens when you are transmitting a rectangular pulse in general. This is your T1 and this is your T2. Suppose it is 1. Then what will be the transfer function of PT? Magnitude response of PT, it will be PF. And we know that every gate pulse is represented by a sinc function in frequency domain. When this sinc pulse is passed through a band pass filter, the band pass filter limits this PF by finite 1. That means if you pass this, you will get only this section supposed to be. Only this part. This is an example. This is not the exact one. I am just trying to say that when any pulse is passed, any finite pulse in time duration. When finite in time duration means infinite in frequency domain. When this pulse is passing through this band limited channel, the pulse also bound in frequency domain at the output of the channel. This is a channel having impulse response HF. The incoming signal from this side, left hand side, is infinite band, and what you are getting here, finite bandwidth signal. So when you receive finite bandwidth signal at the receiving end, and when you convert it into time domain, what will happen? The pulse, actual pulse, will become duration of infinity, from positive infinity to minus infinity. Initially your pulse was PT, but after passing through the channel it becomes PT, which is of infinite duration. Now continuously the pulse is incoming at the transmitter at the input of the channel, and what happens is, this is the first pulse, this is second pulse, this is third pulse, and in time domain what will happen, that these two pulses will become interleaved, and because of this interleave you cannot this ISI will be more elaborate in the digital communication, where there is a special topic which describes ISI. But right now I will not explain too much about the ISI, but I just want to say that because of the band limited phenomena of the channel, the pulse gets flattened in time domain, and it becomes the finite time domain pulse will become a infinite duration pulse at the receiving end. Okay. PCM channel are band limited. The received waveform are distorted and they extend to the next time slot. Which I am saying that extended to the next time slot. The one time slot, this pulse is interleaving to another, and this is in another, and so on. Okay. Resulting an error in the determination of the received bit. You cannot predict. For example, if I want to calculate the sample value at this time interval, we cannot say this sample belongs to this pulse or this pulse, and due to this uncertainty, we will get an erroneous output. Okay, then advantage of PCM: it increases the capacity of single telephonic channel over the cable by multiplexing, and PCM is used for storage, cryptography, and other forms of digital processing. Now come to the next point, which is the bandwidth of the pulse code modulation. The calculation of bandwidth for PCM is very simple. Now let us consider a block diagram of sampler, which is the part of the receiver, and that empty is passing through the sampler. we know that FM is the highest frequency content of FM. Highest frequency content is FM. That means MT is band limited to FM. Then required sampling rate, which is minimum required sampling rate. Minimum required sampling rate will be equal to twice of FM. Point to be noted, this is the minimum sampling rate, that means Fs should always be greater than or equal to twice of FM. Correct? Now the sampling rate at the output of the sampler will be twice of FM. Minimum. This is minimum sampling rate at the output of the sampler. That means sampler is producing twice of FM samples per second. Now let us consider that the output of the sampler is passing through the quantizer plus encoder block, and let us suppose that encoder converts or represents one sample by n number of bits. One sample is converted by the encoder into n bits. In the previous example, we have considered that one sample is converted by 3 bits. One sample is equal to 3 bits. Now, total number of steps of that encoder can handle will be 2 to the power 3. Now, let us consider in this case, as one sample is converted into n bits, then twice of FM samples per second will be converted into n into 2 FM samples, bits per second, n into twice FM bits per second. Now output bit rate will be twice of n FM. You can say that twice n FM bits per second is the output of the quantizer plus encoder block. Please point to be noted, this is the minimum required bit rate. Now you can minimum bit rate at the output of the encoder. Now let us suppose that FPCM is the bandwidth of the pulse code modulation signal. Then the output bit rate will be twice of FPCM. Now comparing these two bit rate terms, that means twice of FPCM with twice of NFM, which is the output bit rate, minimum output bit rate by the encoder, given by the encoder. That means twice of FPCM will always be greater than or equal to twice of NFM. Okay. Why this greater than or equal to? Because twice of NFM will be the minimum bit rate. Then FPCM will be greater than or equal to n into FM. FPCM is greater than or equal to n into FM. So the bandwidth of the PCM is NFM, Hertz. Now if someone wants to calculate the output bit rate, it will be given by NFM, which is the minimum bit rate. So above term is bandwidth. Bandwidth will be greater than or equal to NFM Hertz, and the output bit rate is twice of NFM. So that's it. This is the final topic of PCM, which is the bandwidth.